day 4 was easier than ever. Clean 4 hours and 41 minutes to solve. Trivial, basically. Across, I don't know, 8 sessions probably. The point is, it was easy, okay? Don't worry about it. So we have a bunch of letters here in a grid, and it's the sample's 10 by 10, but there's a bunch of Xmas's hidden inside. So you have to just basically just figure out how many Xmas's there are, right? Yeah, there you go, 18 of them. And here's a little easy mode version where it has Xmas here, for example, Xmas backwards here. You got to just calculate all of them. Easy, right? Easy. Very easy, actually. We're gonna look at part 2, actually. No, well, okay. I don't want to show you part 1 because it's the same thing. It's this whole logic, and I couldn't figure out a nice solution. But look at this. Okay, don't worry about this. Okay, this is not what I would call idiomatic, but it's what 10 lines, 20 lines. I'm a good programmer. So the idea is, all right. My logic was basically I just have to figure out how to get the horizontal characters, right, and then I can reverse them to make that's one horizontal check. Then I can use these transpose and reverse glyphs to to shape the glyph in a not glyphs shape the table in a different way. Easy, right? Easy. Let's if we can imagine what that would look like. If I have a oh, I had this earlier. Hold on. There's a way to plus 48 maybe 0. Is this if I were to show this to you, would you see my height here? 0. Yes. Okay. But if I want to do 90, 94, 97, 90, actually, I have an access code. You can't see it now. I upgraded my thing. Look at this. 97 is actually the answer. 90. I was so close. Look at that. And I happen to know. Due to some education on my part, there's 26 letters in the alphabet. So if I do 26 plus this, look at that. We got ourselves the makings of a grid. My dearest kitten is Katie. All right, no problem. Problem solved. So now we can just make this as a grid, reshape it into let's say 5 by 5. Range, and then reshape again. There we are. Negative it. This is nothing. Easy. She's hold the phone. I'm gonna pause for a second. Pausing. The easy part here is we have our grid of letters. Oh, sorry, I should clarify. This is a range. I can actually do the little F1 here, so you should see the bottom. Perfect. So this is the range. So range of 4 gives you the numbers from 0 to 4 inclusive, or not inclusive, exclusive, I should say. Then I'm adding it to the result of this magical glyph, basically. It's not actually an null character. You can add a code point to it. So 50, I don't know, the 50th ASCII character is 2, I guess. So then I'm adding the 97 ASCII character to every single one of these numbers, which gives me the alphabet, as you saw, right? As you saw, top one up here. And then I'm reshaping it, which takes I don't know how to rephrase it, but you can imagine you give it a new shape. So if I want to have like a 2x2 grid and it'll cut stuff off, I can just do this. So there's 2x2. Excellent. So now we have this. So now I was like, all right, I just need to check this horizontally and then check it backwards. And I can reverse I can reverse the whole thing, I think, just by doing this. Yeah, so now A is on top, and then A, B, C, D, E, F, G, H, I, G. So it's perfect, perfectly reversed. Then you'll see at the top here, if I go back up, I did some stuff to now do each. Once I had the grid of okay, well, I should clarify that too, but then I reversed each individual row too because I wanted A to be on the right instead. So let me see if I do this. If I do this, you'll see that A will be back at the top, but it'll be in the. There we are. So in this case, A's at the top again because I didn't reverse the whole thing. I just reversed each individual row of things, and then I reversed it. Now ABC, because it's a 5 by 5, ABC is to the left now. Then I once again reverse that or something, something like that. Now it's all kinds of messed up. So now these are the columns. This is A, B, C, D, F, G, F, I, and then on the second one after that, I don't see it actually, but it's somewhere in here. It's somewhere in here that I also do the reversed version of that. You don't think it'd be too hard to see just visually because there'd be a whole glyph? This really. Oh, that's not what I'm doing here. There's these reverses. Excellent. There's these reverses that I'm doing. So anyway, what this the solution is actually doing is it's taken our width of numbers here. So in this case, lines, we have our input. I should once again clarify the sample. A sample on our day 4 here is as a 10 by 10 grid. So I get the length of lines because it's a square. So the number of lines is also the width. Then I say they give me the range from 0 to 10, which is 0 to 1 or 0 through 9. Then for each one of those, I then take the one number, digit 1, and again I'll clarify that too because that was cool. It was look at this. I take one number, 1, 2, 3 example, and then I reshape it into a list of 110 things. So I'll have 10 10 by 3s, or what, 10 1, 2, 3s over and over again. And again, I can make that 10 dimensional or something, 2 dimensional, but a grid. And I could even go one step further and make it like a 2 groups of 10. But I'm not gonna. Oh my goodness, my cat is chewing on some netting, which is very safe. And then we have so we have this number, right? So we have from the lengths of 0 to 9. For each one of those numbers, we then repeat that number that many times. Sorry, not that many times. 10 times. We're going on 10 here. Then with that number, which is a constant number, I guess in this case, we want to. Even better. I should even clarify once more that if I do right shift down here, right shift, perfect. This is actually equivalent. I came back to it and tied it up a little bit. So I'm just going to explain this one, and we're going to ignore my messy one up here. This is the same idea, right? Where I have the range of 0 to 9. And for each one of those numbers, I repeat that number 10 times. Then I take the shape of that, which is just 10 ones, so it doesn't really matter what it is. I go through every element of it, combined with every other element of this. It's called table. I can show you. Table, which it just puts an f, the function, between every other function. So I've done this 17 times, but 1 plus 4, 1 plus 5, 1 plus 6, 2 plus 4, 2 plus 5 goes down here. I don't know if you can see my cursor. So that's what that is. It doesn't matter what the actual number here is. It really doesn't. I don't think. Well, you just see my answer is still being correct no matter what I put in. It just gives me the I can actually put if I go down here, I put the character null. It really doesn't care, right? Yeah. See, it doesn't care. So then I make a table this. So again, if I do this, what happened? Cap locks. Cap lock was on. Perfect. So now here's our grid of let's say 10 ones, right? I want to make these a table of himself. Yeah, it's like a table of just ones, right? Then we go table 6, right? 6, 4. There it is, 4. And then we want to look at itself. So again, table is taking for every possible combination of 1 to 1. Then it's just returning the function 1, which is a constant function. In this language, you can make an anonymous function, and it'll be ignore the argument, just return the number because it's easier to work with that way. And table, like I said, takes 2 things. There's left and right, I guess, and we're ignoring them. But we use swap here to take our single variable and single variable, single number, and pass it as both arguments left and right. So you can see here, we're not swapping. We're not swapping because this is a binary function, I guess. Yeah. We're not swapping because it's a single monadic function, and you can see here 1 plus 1 is 2 because 1 plus uses 1 plus itself. Well, now I'm dead on that though. I'm dead on that because shouldn't table give me a function that has 2 arguments? Oh, because I'm applying it monetically. If I gave it this, if I gave it 10 or 110 or whatever, it doesn't matter. It would be the same. Yeah. Okay. So this is an example. So this is my function. This is my like func right here, and the func just gives me 1 back. Constant one. Easy keyboard. There you go. Same thing, right? So our func here is a number that only gives me 1 back. This is again constant function, which is like a modifier that just says whatever the argument is, give me back the number. Like always in Elm or const in Haskell. I'm not sure. Anyway, so we're going back here. Now we have our 1. 1 table 4. 1 table 4. 4. If you were a table, you'd be on number 4. Excellent. Yes, so we have our grid. We'll go back to right shift here. And we, with our table, we then do some sort of 2-dimensional rotation. I've gone through this a million times. I don't remember what it does. But we're doing under this. Okay, well, I'm not going to try explaining this because frankly I can't remember. You know what? We're living in the present day, so let's just figure out what it would do. If you were a computer, you look at this and you'd be like, hey, that's not too bad. We're gonna call this 10. We're gonna give it a 10 number, and this is exactly the same as before. Oh, but then I no. It's a great question. There it is. Easy answer. Okay, we're back. So this is this function is a transpose. I can give it 2 axes. So what am I looking at here? I don't know. I don't know. This is I don't know. I don't know what it is. This doesn't here, let's does it flatten it? Surely. I guess I don't know. Okay, let me might be easy to tell. 9. Okay, how about ID? There you go, because this is the right argument. This is the left one, but that doesn't matter, I guess. So now we're gonna reverse them. Oh, so this is saying this. I don't know. I don't know what it's saying. Okay, some of the axes and transposition. Let's just imagine that it makes sense to everyone. One moment, please. Well, kitten continues to freak out. I don't know why I'm anonymizing the cat as if as if A, she's a person, and B, it doesn't matter what her name is, because you don't chat. Anyway, so I've given up on trying to figure out what transposing does. I'll have to look at what the axes do and stuff. Who knows? All right, it might as well do nothing, but it does something important. And the point is, we transpose it or something. No, it puts 2 axes on the start of it. Whatever. All right, whatever. Good explanation. And then we does it? Where's my under? There it is, under. So this again does is, I don't think this will compile, will it? It obviously will. This is saying do this thing, do this transpose, apply this function to the results, and then untranspose it. But goodness gracious, what is this doing? It's obviously making a flat, right? It's making a flat. Wouldn't that be the same as this? Oops. We're okay on that, I guess. 1. But I wouldn't. Don't know. I must have taken this. You know, I must have taken this from the grid. Actually, let me pull us over on this. Let's figure out this. Replace. Place. Is it somewhere? Grid table. It must be. If I scroll down. Grid. Table. Update. It's modify. Update. Modify. Same idea. There it is. There it is. Look at that. I didn't. Excellent. Good. I didn't come up with myself. I pulled it off of a BQN crate, bacon crate, because I just recognized. Well, I don't know. Universal logic. I'll come back to it. You know, we'll come back to it. This is day 4. We're making good progress. We're gonna come back to that later on in a different day, and I'll have a way better understanding. So we're gonna just hard code the result of whatever this number is to if I could, I bet you if I had different numbers, hold on. This is because we're all just learning anyway, right? Give me this. Does this tell me anything? We're gonna reshape it to 5. No. Okay, good. What does this do? AG MSY. Well, okay, well, not obviously, but it gives me this, right? The AG MSY gives me the diagonal. But why does transposing 0 give me that? Do I transpose just the 0 axis? Nothing. It does nothing. It does it? This is ABC? ABC? This does nothing. 1, 2. This transposes the. Oh, it's not even transpose. It reorders the axes of x as per the axis indices in y. So it puts the 1th index first. I'm not going to pretend to understand again. Because what is axis? Let me tell me the number of axes. What is axes? Axis rank? That's length plus conjugate. No, I don't know what conjugate is. That's fine. M this is shape. That's the depth. Rank. Isn't one of these? It's not this. It's not this. Right. This is shape, depth, length. And this is conjugate. Oh, this is rank. Oh, it's plus. Rank is the number of dimensions. Okay. So if I do this, there's two ranks, I guess, which is number of dimensions. But I'm reordering the first dimension becoming the first dimension. The second dimension to become the first one. This is the equivalent because otherwise it has to go. Is that why I complained with this? Because it doesn't know where to put it to? Okay, well, that's a good question. Does it say? Does it talk about how the? Hold on, I'm gonna pull this over just for a second. I'm sure I'll be pulling back in right away. It'll. Oh, it exchanges to. Let's transpose. Okay, hold on. Transposing tensors. I don't know what tensor is. A lot of. Oh my goodness, a lot of words. Okay. For each index in something. Axis of I. Multiple axes can same. Oh, this is important. Multiple argument axes can be sent to the same result axis. I guess result axis is the leftmost argument. In which case the axis that goes along diagonal of x. In which case that axis goes along the diagonal of x. And that results of a lower rank than x. See the next section. Okay, I don't know if I have time to read this online. Yeah. Thanks. All right, this is well, we'll have fun. We'll come back to this after. So, point is, this has been very easy, right? We got our diagonal, and we just say, okay, you know what? For the whole range of this thing, you're going to be 1, and put it back in, and then thanks to this, we have this diagonal range, whatever, right? Because you'll see. Actually, I won't show you here, right? But we have this diagonal thing, and then we want to say for these diagonals, set them to some other number. So I'm gonna do. I think I could just say repeat 5 ones, right? 5 ones, and under is k or something. So it's gone. Okay, I'll just change this to z to make it easier to see. What? Oh, not z. Sorry, z. So now we have z's across our diagonals. So what this is doing is it's saying take the diagonal of this and replace it with a 1, because I have this many ones. Length is 3 in this case, so 3 ones. So len is here, and I tried making it smarter basically because I wanted to remove or reduce duplication, but I decided that was not worth it, and the legibility here was better. But that's what's happening, where you can see len is the repetition of this thing here, or x is the repetition of this thing, and then same with here. And then I once again shift it by shift the whole thing, which is again not this, you'll notice, but the outer things. Well, no, now I'm thinking again too. Oh right, okay, right. Shoot, I forgot the cells. So this len is our range, right? So this in our case down here is 3, but up here it's 10. So this is range of 0 to 10, and then I take for each number in there, I shift over that number. I shift over that many times because the star is repeat. I go up here. This is great. So this is saying, in this example, it's saying add +1 4 times, because this 4 gets passed in as the argument of this, which means repeat 4 plus 4 times. So it's 4 plus 1 is 5. Then 3 more times, 6, 7, 8. Confusing. Then this is a constant function scenario. Yeah, I don't know. Doesn't make sense to me yet. But now we're going back to this example. So we're here. We have our diagonals that are swapped and shifted appropriately. Then I do the opposite for this side, where I do the transpose. This is actually reversing, and then I transpose to have like the diagonals switched, and then reverse, like I said, with the ABCZ thing over here. Okay, good. This is a great explanation. I'm glossing over it, but this is the easy part. So for the left to right, the horizontals, I just have to. I have the original lines, right? Like this is just the original line. Okay, I'm gonna go to sample here. Just the original lines. I'm gonna go back once again to this. You can see it's the original lines in the sample. Then I just see for each one of these, where if you'll see this is actually find, where it's finding the substring, right? So substring can only contain string at the 4th index, 0, 1, 2, 3. So this guy is where S is, and then it doesn't include the rest of them because string cannot possibly, like the 5 characters, 6 characters here cannot possibly start at like ring because there's not enough characters. So it just omits them. It's the way I do, I can do, or it can do, or whatever, where it suggests. I think maybe it'll say somewhere in the docs, but basically you take after, because take as a fill variable and replace it with zeros, but it doesn't matter. So and I also here I also enclose Xmas in a list. I don't think I have to, but that's what I do. Why am I getting the wrong answer now? Oh, because I sampled it. Okay, so I can actually go back here. So yes, so we just basically say for every time there's a 1 in this example, we sum them up. And then that goes for every single line in ones. And then for all those sums, we sum up. And that gives us a total horizontal left to right Xmas's. And likewise, we reverse every single... Does this actually do anything? Oh, yes. Sorry. The lines in this case is whatever, is the first sample. We reverse everything. So the sample's backwards. And we do this exact same thing. And here, I don't know why I have to merge these again, but I think I do have to. Yeah. I don't recall why I had to merge them, but I did. And I just transpose the lines, which I think just basically rotates them on in this example here, the Z would say same place, I think, but the B and E and U would change place. I don't know. Anyway, that's the top to bottom. So top to bottom and then bottom to top. And then this is the same thing, but now because we're doing the diagonal from the, instead of like the Z's on this angle being replaced, it'd be the Z's on this angle being replaced. I do that, and I just count them up. And then these are all sums or whatever, and I just have to sum all these up. I don't know if I can show this easier. You can see there's 217 whatevers. I can sample it up actually. Let's say there's three vertical or horizontal ones. the sample, you can see there's, I can do the X actually, I was doing this here. I just search for X, perfect. There's one, 2, 3 horizontals, and then what's my number for 2 right to lefts. So there's 2 X's going horizontal backwards. 1, 2, that's it, 2, just 2. So you can see that works pretty well. And again, no worries if you're not catching up, because it's definitely a mess. My error is pretty rough right now. Oh, because I didn't format it. Excellent. We'll get back to this another time, but I added a function to make my prints a little easier. There you are. So that's our solution to these to part 1. Let me show off what my part 2 solution is as we approach minute 25 in this video. So now part 2, same idea, but part 2 is actually it's actually a little different, where they're like, oh, actually, Xmas doesn't be backwards and forwards. It actually has to be a cross of XMAS, or not XMAS, but it's actually MAS with an X dash. You could see. So I thought it was a clever trick of the wording. Now, MAS or SAM can be shown. So, for example, MAS makes a cross, and it also does backwards, where it's SAM and SAM. But they hide it pretty well in the example here. But there's also, this is a MAS and MAS X. This is a SAM and a MAS X, right? There can also be mixes matching, so SAM and then MAS. So, you know, they mix it up. But the point is, you can have crosses of MAS, no X's at all. So my original solution was to say, okay, that's not bad. That's basically the same thing I have here. So instead of just checking, instead of merging the overlaps or whatever, instead of checking for Xmas, I just check for MAS or SAM, and then only the diagonals, because I don't care about the horizontals anymore. And then I would cross-reference like which X on this diagonal, like on the top left, the bottom, you know, top left down, has a that is in the MAS or SAM. And I do the same thing with the down, top right down diagonals, and figure out which A's are overlapping. And then it took me literally 4 hours, maybe 3.5, I guess, because I going part 1, to figure out that couldn't possibly work, because coordinating 2 matches on one line wouldn't work. You can see that in the full demo or the full, you know, play session or whatever that I record. But the idea is that's not possible. So I was like, okay, what else could be the trick? I'm like, hold on. There's something called window, which I've used before, obviously, but where is it? Range or something? There you go. Here it is. Range. So you pass 5, and then you get a range of all the possible windows, like overlapping slices from 5 long. So this is the first 5 characters, then it'll be the second 5 characters, and then the third 5 characters. So ABC, and starting with B and starting with C works, and it works for 2 dimensions too. This is the number 0 to 9, which is 0 to 8. And then I reshaped into 3x3 groups. So I can go full screen on this, and I can get rid of this guy. I'll never see it anyway. You can see that we have our 0 to 9, or the range of the first 9 characters, sorted in a 3x3 grid, and then I turn them into a 2x2 grid. And what I didn't fully understand how to do was merge these in together. And I think I definitely do it in my code, but I think the answer was literally just it wasn't just merging, right? It was like doing this or something. It was something like this. There's something like this where I had to combo them together. Oh, it was insert. It was insert. There we are. Maybe. Did that actually do anything? Yeah. So you can see that the notch is going away. There's a zooming issue on my. There you go. If I hit control now, they've gone away. And I might have to do it another time. Right? Yeah. That of course loses the grouping together. So this is good as it is. So now this is just a bunch of all the windows. And if I were to get the first one of this, yeah, this is the first group, the first window, you know, like the grid that's here. Now I got the second one. You'll see that it should be 1, 2, 4, 5. Nice. And then the next one will be 3, 4, 6, 7. Excellent. So it's like a little viewport or window that goes over this thing. So once I had that, the rest of it was just a matter of doing the little Sam Rexmus lookup inside there. So again, this is our big mess as we saw in part one. This is the same sort of thing, but I realized, that I realized the mess of it. So I had to rewrite it to be something nicer, and that I didn't need to do this per window because I was doing this shift per window, and it would take forever to evaluate. So I just had to do it once, which is cool. Fun little realization. So this is again what this is doing is it's saying for every the diagonal indices is the whole. I guess I can show you too. That might be too rough to show in one window here. Or was wrong. I don't need to know that anymore because we're solving that. Perfect. So now you can see if I zoom way out. Well, not going to be convincing, but I scroll up. All the diagonals, well, whatever. Actually, each one of these rows is the diagonals for one set of windows. This is the bottom left diagonal because it's a window 3x3, right? So one diagonal, two diagonal, and this is a full on 3 diagonal, and then 2, and then 1 again. And I only actually care about this full one. So you'll see that I literally just grabbed the one that's in the middle, and I called it APOS. Because I have to check if this character. So find A tries to find A in only this character or only these two characters, etc. And I just do a print or whatever. Not print, what is it? I don't know, just the max or whatever. I don't know what. I try to find everyone, and it only shows the results if there is one, and there only could possibly be one in only the second, the 2th index every time. So I just pull it out, and then what I do is I have to figure out if both of them are not empty, because there can be cases where, I guess show it. If I show, so sometimes there'll be a match in the one, like the top left diagonal, or in the top right, the downward diagonal, and but the ones I want is when there's both diagonals have an A in the middle where I want A being the Sam or max, not just an arbitrary A. So I just figure out if the length of them are I calculate the length of them because this is a 0 length thing, and this is a 1 length thing. I couldn't figure out I didn't want to do a nicer thing because I wasn't 100% sure my solution that they wouldn't only be one number or whatever. But anyway, I just find the max, the min, I add them together basically, and then I have to do the get from them basically, to just because it's a list of things that I'm doing, I guess, and then if the length of it, the ending of these results is 1, then it's valid. Otherwise, it's 2, and that's actually it. So I do the per window on each one of these results. Oh, I should say I also join them with the I enumerated them in Python. You know, you can do the if I scroll out on this. If I this little bit here is basically like saying I don't know if I can make this easier, but you know, for I in values or something, right? Print I. Well, or val, I should say, right? Now I had this. This is my Windows. Oh, I can do Windows, sure. But then I changed it to enumerate. I don't know if this is any obviouser, but this is what I changed it to. So now I have a train of taking the values and then the length of values with the range of it, which is 0 to the length of values. And I pair it with each element of that. So 0 goes to the first element, 1 goes to the second, etc. And I do that just for logging. I don't think I use it here ever now. Yeah, it's not used at all. But it was used for printing. Excellent. Sweet. Okay, well, actually, since we're going in further here, a nice pattern I was using was this assert function, which just complains or throws an error, like an actual error, if this number is not 1, which is to say true. And so you can say like it is it not 1? Okay, 1. It works fine. If I change to 0, you'll get an assertion error. But this message here, this string, does not get the actual value. It's a constant function or something. It's just a message. So you can't actually like You can't dynamically set a process. So I just process the number first, and I say like, well, you can see right here. I say here's the error message, which I build up based on the answer, and then only show it if the error message, like if the expected is not true. I compare the answer to the expected value, which also serves to work as like a solution thing, and then if not, to the error. And finally, I do the happy print. Yeah, yeah, cool. Very strong. Thanks for watching. Hopefully, I'll try part 5. Part 5. I'll look at it right after this, but we'll see how it goes.